What would happen if every planet in our solar system crashed into the sun at the speed of light? Which planet would create the biggest explosion? To find out, I recreated this experiment in Universe Sandbox. Instead of testing the entire solar system at once, each planet is tested individually in a separate simulation containing only the sun and a single planet. This allows every impact to be compared under the same conditions. Mercury becomes the first planet in our experiment. Before the collision, the sun's surface temperature is a steady 5,780 Kelvin. But the moment Mercury strikes at the speed of light, everything changes instantly. The sun's surface temperature surges to an astonishing 1,778,403 Kelvin. The impact doesn't stop there. A burst of solar material is blasted into space almost immediately, sending glowing particles racing away from the sun. As the simulation speeds through the following years, the sun slowly begins to recover. Its surface temperature steadily falls, and after many years, it eventually returns to a level close to its original state. Even the smallest planet in the solar system can produce a spectacular event when it is accelerated to the speed of light. Next is Mars, the red planet. This time, Mars is launched into the sun at the speed of light. The impact is far more powerful than Mercury's. The sun's surface temperature instantly rises to approximately 3,399,561 degrees Celsius, causing its color to shift into a brilliant light blue. At the same moment, glowing solar material is blasted into space as bright particles race away from the sun. As the simulation speeds through the following years, the sun gradually cools, and its surface temperature eventually returns to normal. Now it's Venus's turn. As Venus slams into the sun at the speed of light, the sun's surface temperature skyrockets to approximately 31,945,704 degrees Celsius. But this impact has a completely different outcome. Instead of surviving the collision, the sun instantly breaks apart into countless glowing blue, gas-like fragments. The debris rapidly expands into space, and as the simulation continues, the fragments gradually disappear. In the end, nothing remains where the sun once existed. In this simulation, the impact from Venus completely destroys the sun. Next comes Earth. As our planet collides with the sun at the speed of light, the sun's surface temperature surges to approximately 43,006,221 degrees Celsius. The result is nearly identical to Venus's impact. The sun instantly shatters into countless glowing fragments that rapidly spread into space. As the simulation continues, the fragments gradually disappear, leaving nothing behind where the sun once existed. In this simulation, Earth's impact completely destroys the sun, just as Venus did. Now it's Neptune's turn. As the giant ice planet crashes into the sun at the speed of light, Neptune's average surface temperature rises to approximately 679,951 degrees Celsius. The impact produces a very different outcome. A massive cloud of thick, glowing fragments is blasted into space almost instantly, leaving behind a light blue, glowing cloud-like remnant where the sun once existed. The sun itself is no longer visible. As the simulation continues, the remaining cloud-like remnant ejects another huge wave of glowing gas into space. Eventually, the glowing material fades away, leaving behind a colorless Neptune in the place where the sun once existed. Now it's Uranus's turn. As the ice giant collides with the sun at the speed of light, Uranus's average surface temperature rises to approximately 4,327,496 degrees Celsius. Like Neptune, the impact tears the sun apart. Massive, thick cloud-like fragments are blasted into space, leaving behind a glowing light blue cloud-like remnant of Uranus, where the sun once existed. The sun itself is gone. As the simulation continues, another huge wave of glowing gas erupts from Uranus. The remaining planet gradually changes into a glowing yellow molten world. After a few months, its average surface temperature drops dramatically to around 314 degrees Celsius, leaving Uranus behind in place of the destroyed sun. Now it's Saturn's turn. As the ringed giant crashes into the sun at the speed of light, Saturn's average surface temperature rises to approximately 5,711,850 degrees Celsius. The impact is unlike anything we've seen so far. A massive blue cloud of thick fragments erupts into space, while at the same moment, a narrow wave shoots outward from the collision, appearing powerful enough to sweep across the entire solar system. As the simulation continues, both the expanding wave and the cloud-like fragments gradually disappear. In their place, a glowing yellow molten Saturn remains where the Sun once existed. After 2.31 years, Saturn cools significantly, with its average surface temperature dropping to around 682 degrees Celsius. Finally, it's Jupiter's turn. As the largest planet in the solar system collides with the Sun at the speed of light, Jupiter's average surface temperature surges to approximately 4,910,629 degrees Celsius. Just like Saturn, the impact creates a massive blue cloud of thick fragments, while a narrow wave rapidly expands away from the collision. As the simulation continues, Jupiter remains behind, glowing like a small star with an average surface temperature of around 5,200 degrees Celsius. Unexpectedly, its temperature later spikes to approximately 14,480 degrees Celsius before beginning to cool. After a few days, Jupiter's average surface temperature falls to around 414 degrees Celsius, leaving the giant planet where the Sun once existed.